So this is the section on exponential and logarithmic equations, and we have only one property here, which of course, yeah, this is really self-evident almost. And I just want to do a few examples here. It's also a relatively short section, so solving an exponential equation. This is interesting. This one right here, solve the equation 10 to the 2x minus 1 equals 3 to x. Notice that the bases are not the same, so I can't just do something there. But here's the trick. Take the logarithm on both sides, and then you can see what happens is and it doesn't matter actually which logarithm, it doesn't have to be base 10 or 3, in this case they use base 10. It could be any other, but then what happens is now you use the power rule, so the 2x minus 1 goes to the front, and here the x goes to the front, and we have log 10 times log 10 over here, and times log 3 over here. I meant to cover it like this, times log 10, there you go. Now, log 10 itself is simply 1, because 10 to the first power is 10 itself. But even if it wasn't, it wouldn't be bad at all, because let's say this would be log of 20. Well, you get a number, and you divide it into log 3. So, again, not bad at all. So here, at this point here on the next line here, so the log 10, of course, is 1, and the log 3 here could be already written as a number, but they just leave it this way. And then they subtract x here, and then they have x times log 3, and then they factor out x, and then divide by this one here, and you come up with 0.6567. And because that's a numerical answer, we can check that. So what I could do with this one here, 0.6567, is I plug it into the original equation, and then I hopefully don't lose my calculator. And then, so I'm on the right-hand side, that's quicker, so I'm going to do 3 to the 0.6567. And I come up with this one on the right-hand side here, which means on the left-hand side I ought to come up with the same thing. So it's going to be 10 to the parentheses 2 times x, which is now 0.6567. And then it's a minus 1. There you go, minus 1, parentheses. And I come up with the same answer, 2.057. Notice that in the back here, they're a little different, but that's because the answer was actually truncated. You know, it just goes on and on. All right, let's do example 3. Solving an exponential equation. This one here actually, looks a little involved, but it's actually not bad. Just subtract the 6 from the 24 to start with. You know, you get this one here, 18. Ooh, then you have divide 3 into 18, so you get 6. Then you take the natural log on both sides, which pulls the 2t to the front. Of course, ln e is simply 1, and then ln 6 is a number, and then divide by that 2 that you have here, and there's the result. All right, example 4, continuous compound interest. So you read in the book, respectively, when you look on number file, on that video that I recommended that you watch, that e actually came up in the 17th century when people figured, oh, how can I get the best interest from a bank? And so Jacob Bernoulli said, I'm going to take this interest formula, and if I reduce it to virtually, I get interest all the time, of course at a much, much smaller rate, then actually I come up with this exponential function. So here it is. So it says, suppose a bank pays interest at a 5%, 5% rate, initial deposit of $1,000. How long does it take for $1,000 to grow to a total of $1,200? And this is compounded continuously, which means use this equation rather than the other equation you had seen before for compound interest, so the one that precedes the exponential. So for a total of 1,200, and then plug in these numbers, 1,200, 1,000, 0.05 here is the rate times time. Divide by 1,000, take the natural log on both sides, which pulls the 0.05t to the front. ln e again is 1. Divide by 0.05, and apparently it takes 3.646 years. All right, I want to do example 6. Bacterial growth. And that, of course, is relevant. In the spring of 2020, we have this coronavirus, and even though a virus is not a bacteria, but they do grow exponentially, at least the infection does grow exponentially. And that's something really for people to understand, that this goes huge. So, because that's what the exponential function is doing. So here it is. P equals the population equals the initial population e to the kt, where the value k is a constant in front of it that depends on the doubling time. So it says population, initial population is 10,000, doubles every 10 hours, which means after 10 hours, you got 10,000. Oh, wait a minute, you got actually 20,000 because it doubled. The initial one was 10,000. After 20 hours, you don't have 30,000. No, you have 40,000. And after another 10 hours, after 30 hours, you don't have 50,000. No, you have 80,000. And then 160,000. Every 10 hours, it's doubling that. So here it says, find the population at time t equals 0, find the value k. What is the population at time t equals 20? So they set it up here. Here's that equation. And the first one is really easy. You know, initial population is 10,000. Set up the equation. There it is. Now plug in the second part, plug in the numbers. Initial population, 10,000 here, 20,000. That's what it said. That's what we would have after 10 hours. So we put in a time of 10 hours here. And actually, this one right here, you know, written from left to right. This one is here actually written from right to left. Oh, well. So we have this one here, divide by 10,000, we get this, take the take the natural log on both sides, which of course again will give us 1 right here, and here we have ln 2 divided by 10, so k comes out to 0.0693. K is the growth constant. And so the expression is like that. Then put in 20 hours, well, actually turns out we already knew that answer from earlier. It's 40,000, right? All right, I'm going to do that on Desmos. So let's see, I'm going to start with a table here. And what did I have here? 0 hours, I had 10,000 of them. Does it not like the 10,000? The way I wrote it? Oh, it didn't. Okay. 10 hours, it's 20,000. These are the 3 data points it actually gave us in the problem. So 20 and 40,000. And then I already know what the exponential is. Actually, let's see. Actually, let's have a graph here. Where here they are, these 3 points. I already know how it looks like, so I'm going to have y1 is proportional to an initial population. I think I just call it p, I guess, or capital P, times e to the kt, respectively, in this case, x1. And there we go. We just saw that k itself here. I'm going to push this a little bit over. So that k here was actually 0.0693. We just saw that the initial population is indeed 10,000. That's what the exponential calculated. And then, oh, I just see that it's actually off the screen. I apologize. So there we go. It's a little better this way, right? I'm going to push this one over. So the 3 dots actually, I guess one of them was a little off the screen, but here it goes up exponentially and it just grows. You know, 40 hours, it's 160,000, as I said. And how about a week? All right. Well, a week is going to be 170 hours. So let's look at that. Boy, this is off the chart here. This after 1 week, look at this. This is insane. I can't even get there. Let's see. This is just 100 hours, okay? At 100 hours, I'm at 10 million. That's 1 times 10 to the 7. And yeah, an exponential is just incredible. I'm just zooming out and zooming out and zooming out, you know, and I tried to put my point on here. And let's see, down here it says, oh, that's, I don't know what that, yeah, it just goes up and up and up. I mean, this is the exponential here. And that's what we have with the virus, that not that this virus is going up that fast, but the infections do. They go up exponentially. All right, let's go to example 8 is what I wanted to do. There it is. Okay, so this looks a little different, right? So this is actually an actual equation, like a linear equation, what we're going to do, or looks a little bit more involved, right? What's going to happen? What are we going to do with this? And the log is appearing twice. So, and then I have a plus in there, but now we notice that one of the properties of logarithms is when you add the logarithms, you're actually multiplying the stuff that's inside, and that's exactly what they do from this first line here, which is the original problem, to the second line. That plus right here, oops, I didn't mean to be crossed out, that plus right here becomes a times inside the logarithm. So it's log 2x, x plus 4 equals 1. Okay, now I have a logarithm on the left. I'm going to get rid of it by doing exponentiate both sides, I guess it's called. So 10 to this log here, which means that 10 to this, all this log here and stuff like that, well, that gets rid of the log and the 10. So I'm actually back to 2x, x plus 4. Got rid of the log doing that way. Of course, I have to do it on the other side as well. So it's 10 to the first power, which is this one here, 10, obviously. And now I have a nice quadratic equation which I can factor or use the quadratic formula and so on, and I get a couple of solutions. I get -5 and +1. And then it turns out something interesting will happen with these here. One of them is actually extraneous. You know, it already says, it's kind of giving it away. Oh, x equals -5. I don't know about the logarithm when I put that in. And it depends on what you have inside the logarithm. So it turns out actually the 1 will work. We're going to have log of 5 right here when we plug in the 1, and here we're going to have the log of 2, and apparently when I do that I come up with exactly 1. Well, let's check it out. So I'm going to have log of 2, that's the first part, plus log of 1 plus 4. Now on this one here is actually 2 times 1, right? And when I hit enter, I indeed get 1. Yeah, so that's correct. Let's see about the other. Let's see what happens. When I plug in the other solution, -5, well, I ought to have, let's see, where is it? Log 2 times -5. That should not work because that's the logarithm of -10 plus log of -5 plus 4. That also should not work because it's the logarithm of -1. Let's see what happens. And indeed, yes, non-real answer. If I changed my calculator actually to complex numbers, it would actually do it, but we're going to stay with real numbers here for now, for this one here. So logarithms of negative numbers are not possible. All right, got one more example here. So example 9, solve this equation. Again, we have logarithms here, and what we're going to do is we're going to combine the logarithms on both sides to one side. So this one here is being subtracted to the other side. So notice we have a minus here. Well, minus combining or linking the logarithms means that we divide inside the logarithm. So it's x divided by x minus 1. That's still the 2 that we have. 2 is being carried through. Okay, how do I get that now? Well, I exponentiate with the base, which is e, then e to the ln here. They get rid of each other, which means I just have the argument right here, x divided by x minus 1. There it is. And on the other side, I did the same thing, e to the second power. And here it is, e to the second power, 2.71 squared is probably in the neighborhood of 8 or something. And then they solve for x here because this one here looks like a complicated fraction. That's why it's still going to take a few steps, and you can see the algebra here times x minus 1. Get the x to the other side, respectively factor the e to, or distribute the e squared to both of these. Get the x to the other side, subtract, then you have this one here and there and negative and so on, and 1.56. Yeah, let's use the graphing calculator and see how that turns out. So I'm going to take that solution and plug it into the very first one up there. Let's see if that's true. So on the left hand side I simply have ln x. So I'm going to do natural log of 1.1565. And I'm going to come up with this number, and the right-hand side should come out to the same thing. So I'm going to try that. 2 plus natural log of, and this one is going to be 1.1565 minus 1. Well, how could I possibly come up with 0.14 if I'm starting already with a 2, which means this here must be coming out negative, and it will, because 1 minus 1 is 0.15, and the natural log of a number that's smaller than 1, between 0 and 1, will be a negative number. And when I hit enter, indeed it will subtract about 1.86 to come up with the 0.145, which means that the left-hand side right here equals the right-hand side, and the solution of 1.565 is correct. Okay, let's look at a few problems here. I chose, I think on the homework, 39, 41, 43, 45. I'm not going to do them. I just give you hints on how to do these. So here we go. This is number 39. We have two logarithms here. They're linked by a plus. The plus means it becomes a times. So inside the logarithm, we're actually going to have x plus 1 times x minus 1, which obviously is x squared minus 1, difference of squares inside the logarithm. So I would have to take both sides 10 to that, so exponentiate, which still means on the left-hand side, eventually I will have x squared x squared minus 1. What am I going to have on the right-hand side when I exponentiate that? 10 to the 0 power. Well, that's 1. And then eventually, I'm pretty sure you're going to come up with the square root of 2, plus minus the square root of 2. All right, here you're going to, 41, you're going to do something similar. So you're going to have x times x plus 3. And within the logarithm, and then you exponentiate. So you're going to have 10 to the first on the right-hand side, which is 10. And over here, you're simply going to have x times x plus 3. Looks like a quadratic equation to solve. Okay, what happens here? Base 2, that might be actually the change of base formula. So I add this one to the other side and get then log 2 x plus log 2 x minus 3. The 2 would be multiplied because of the plus inside. So I'm going to have x times x minus 3, and then I'm going to have 2 to the second power because of the base here. And I think I'm going to come up with a quadratic equation again. Let's look at Simple Lab. Let's see how they do that. They pretty much will do it in the same way that I just said it out loud. So solve, let's see, what was it again? Log base 2x. I'm going to type that in and stop the recording here while I type that in. All right, if I didn't make a mistake, then I typed it in. Well, I didn't make a mistake. I forgot the equal sign, actually. Let me see if that's where it is. Equal right there, so solve that, and let's see what Simple Lab does with that. All right, okay, so it gets a solution right here. X is 4. They always choose these problems so that you come up with a nice number. Okay, that's not true. Not always, but quite often they try to do that. So let's see how they do that. So they add, just like I said earlier, they add this one here on both sides. So you simply have a 2 on that side here. Then the plus here links these two logarithms to a times. You see that right here. So the plus became a times inside the logarithm. Then they exponentiate it. So exponentiating with base 2 means you get 2 squared on this side here, which of course is 4, and there it is, 2 squared, and there's the 4. On the left-hand side, 2 to the log base 2. Well, that gets rid of the log, so you have this one. You just have the argument, your x times x minus 3, and there it is, and now you have a quadratic equation right there, and you solve, you get 2 solutions, 4 and -1, and just like they say here, that one of these is actually extraneous, so apparently the -1 doesn't work when you plug it back into the logarithm, but the 4 does. Let's see if that's correct. Yeah, that would be log of -1, and here would be log of -4, so that's not going to work. But log base 2 of 4 is 2, log base 2 of 4 minus 3, so log base 2 of 1 is 0, so 2 equals 2 minus 0, so it checks. All right, and here, what did I say, 45. So here you would have to subtract this one from the other side. So kind of like earlier, you're going to get, because of the subtraction here, the two logarithms, you actually get a division out of it, 2x divided by x plus 3, and then equals 1. This one here, 47. Did I say 47, or am I done? I didn't say 47, so 45 was that. Okay, and that's the section.